Alright, so this is going to be a short video on multivariable linear systems and row operations. So this is kind of introducing us into matrices using Gaussian elimination and Gaussian-Jordan elimination. So this should help with that first set of problems. So here we go. So first we need to define what a multivariable linear system is, and that's just when you have a system of linear equations. Okay, so everything's raised to the first power, right? So we know what a line looks like. So like 3x plus 4y is equal to 7. That is a linear equation. In fact, that is a multivariable linear equation. So if I have a system of those, or if I have multiple ones of equations that are like this, that have um, that are all to the first power, um, and I've got more than one variable in there, then this is a multivariable linear system. And while you can use substitution and elimination methods that you've used in the past to be able to try to solve these things, as the number of equations and variables grow, these become a lot more tedious. And so uh, people kind of came up with other methods to try to help this out. So we're going to try to get our system into this inverted triangle method. And this inverted triangle method, where we try to get the leading coefficient to each thing as a 1. So there's a 1 on our x here, there's a 1 on our y here, and there's a 1 on our z. And we're also having one less variable in each row going down at the very least. So this is called row-echelon form, okay, of a system of equations. Later we're going to talk about how we can take this row-echelon form and convert it into matrices. Okay, so that's that. All right, row-echelon form, just as a reminder, all ones for the coefficient for the leading term, and we are dealing with less variables as we go down. Okay, that inverted triangle. Alright, so to get them into this row echelon form, we're going to use Gaussian elimination. So here are the things you're allowed to do in Gaussian elimination. You're allowed to swap any two equations order. You're allowed to switch them places. So if I have them listed as equation 1, equation 2, and equation 3, I can say let's switch equation 2 and equation 3 so that one's on top of the other one instead. We're allowed to multiply any equation by a non-zero number. So I could multiply some equation all by 2 or 3 or a third, whatever it is that I need. And we're allowed to add a multiple of one equation to another equation. Basically, I'm allowed to add and subtract multiples of equations to each other. So here is example 1. We're going to take this system of equations that I have right here, and we're going to try to put it into triangular form. And I'm going to leave this as equations. We're going to wait to turn these into matrices until just a little bit further on. So we're going to start off with this equation 5x negative 5x minus 5y minus 5z is 35, negative x plus 2y minus 3z is negative 12, and 3x minus 2y plus 7z is 30. And remember, my goal is to get a coefficient of 1 in the front and to be eliminating variables as I go down. Okay, so I'm going to start this off by, first thing, I'm going to multiply equation 1 by a fifth. So remember, I'm allowed to multiply an equation by any multiple. So when I do that, that turns this into x minus y minus z is equal to 7. I got negative x plus 2y minus 3z is equal to negative 12. And I have 3x minus 2y plus 7z is equal to 30. Okay, so now that I have a 1 in the coefficients, that's what I wanted to start off with first. I wanted to get this first coefficient to be a 1. Now, what I'd like to do is eliminate the x's underneath this. Basically, now I have my x with a coefficient of 1. I want nothing else to have an x in it. So to do that, I'm going to, from here what we did is we did 1/5 times equation 1. That's what we did. That turned me into here. So to go to the next set, I'm going to take row 1 and I'm going to add it to row 2. When I add row 1 and row 2, I'm going to replace that with the row 2 spot. So when I do that, that gives me x minus y minus z is equal to 7. But when I add these two equations together, I get 0 x's plus y. Add those two together and get negative 4z is equal to negative 5. And I'd also like to get rid of the 3x. So to do that, I'm going to take negative 3 of equation 1, and I'm going to add it to equation 3. So if I take negative 3 times equation 1, that gives me negative 3x plus 3y plus 3z is equal to 21. And I want to add that to 3x minus 2y plus 7z is equal to 30. And what that will give me is 0 x's, y, add those z's up, and you get 10 z's, and that is equal to 21 plus 30, or 51. Okay, so I'm getting closer. I've got the coefficient of 1, I've got no x's underneath, and hey, guess what? I already have a coefficient on a y of 1. I'd like to get the y out underneath. So I'd like to take equation 2, negative equation 2, and like to add it to equation 3. Or basically, I'd like to subtract these two things. And so what that'd look like is negative y plus 4z is equal to 5, and I want to add that to y, 10z, and 51. So our system of equations will end up looking like x minus y minus z is equal to 7, y minus 4z is equal to negative 5, and 14z is equal to 56. Okay, coefficient of 1, coefficient of 1, no x's underneath, no y's underneath. This needs to be a coefficient of 1, so I'm going to take 1/14 of equation 3. And when I do that, that gives me x minus y minus z is equal to 7, y minus 4z is equal to negative 5, and z is equal to, when I divide that all by 4, or by 14, excuse me, I get 4. Alright, so this is putting it in triangular form. It is in triangular form right now. Then they want me to use that to solve the system. Well, I already know that z is equal to 4. Since z is equal to 4, I know that y minus 4z is equal to negative 5, which means I have y is equal to add 16 to the other side and get 11. And once I have that, I can take x minus my y minus my z and say that that is equal to 7. So I'm going to add 15 to the other side, and when I do, I get 22. So my solution is 22, 11, 4. Alright, that's good for example 1. Like I said, yes, it still involves a lot of work in this case, but it's very systematic work, and hopefully you can see that if I had something like 10 or 20 or 30 variables, having a nice systematic approach is going to be really useful for us. So now let's talk about turning our equations into matrices. This is probably something you have done before. Let's talk about what an augmented matrix is. It's taken from the coefficients and the constant terms of linear equations when we write them in standard form. These are standard form. The x's, the y's, and the z's are on, or the variables are all on one side of the equation, and the thing that they are equal to, the constant term, is on the other side of the equation. And we're also going to talk about a coefficient matrix, which is the same as the augmented matrix, only without the constant term. So here is my augmented matrix. It is 5, negative 5, negative 5, 35, negative 1, 2, -3, -12. These are coming from the coefficients. See, 5, -5, -5, 35. -1, 2, -3, -12, and then the last row, 3, -2, 7, 30. There it is, there's my augmented matrix. I can write this as a coefficient matrix by just leaving out the constant part. So 5, -5, -5, -1, 2, -3, 3, -2, 7. We don't need to worry about the coefficient matrix today, or during this particular lesson. We're going to worry about it later on. We're going to have some ways of solving systems of equations by some other methods, and to do that we will need our coefficient matrix. Alright, so now let's see if we can write the augmented matrix for this system of equations. So I'm looking at this system of equations. I see I have 4 different equations. I see I have w's, x's, y's, and z's. So I need to make sure I have a spot for all of those. There's one w, there's 4 x's, there are no y's, and there is one z in the first equation. There are no w's, there are 1 x, there's 2 y's, and there are -3 z's in the second equation. In the third equation, there's 1, 0 x's, -3 y's, -8 z's, and -1. So this has been my w column, my x, my y, my z. And then last, I have 3, 2, 3, 0, 9. There it is. I have written that matrix as an augmented matrix. So how am I going to use this augmented matrix? Well, I'm going to use this augmented matrix to basically help me solve these systems of equations without having to write the entire equation the whole time. So I'm going to use the same operations we used on the equations, only we just use them on different rows of our matrix. So these are our elementary row operations. You're going to see that there's a lot of parallels with what we did with the equations. I can swap any 2 rows, I can multiply any one row by a non-zero number, or I can add a multiple of one row to a multiple of another row. And working with these rows is a lot simpler than dealing with the equations. The operations can things we can do in our head. We do need to record our steps so that people can follow our work, and so that if we make a mistake, we can figure out where it was. Sometimes it is convenient to combine multiple steps just to save some work. It still takes up a lot of paper, so you're going to have a lot of paper handy for this stuff. Alright, so what is row-echelon form? So now that we know how to do these basic row operations, what's row-echelon form? Well, row-echelon form is basically the following thing. If I have some matrix, okay, if there are any rows that are all zeros, it's all on the bottom. If I get to any row, the first entry in that row should be a 1. If I have 2 successive rows with non-zero entries, then the leading one in the higher row needs to be further to the left than the leading one in the next row. So something like this. So basically this is a matrix in row echelon form. I'm getting those coefficients to a 1. Okay, these entries to 1s, going in that upside down triangle fashion that we had before. And just like we had before, if I have something in this spot, there's nothing underneath it, just like we did with the x's, the y's, when we were solving our system of equations. So let's take this system of equations and let's write it as an augmented matrix, and let's use those elementary row operations to see if we can put this thing into row echelon form. So here we are as our augmented matrix: 1, 2, -3, -28, 3, -1, 2, 3, -1, 1, -1, -5. So there we have it. There's my augmented matrix. When we're solving this thing, again, my first thing I want to do is I want to try to get a 1 as a leading term. I already have a 1 as my leading term in my top row. So next thing I want to do is eliminate all the entries underneath. So first we get to a 1, then we eliminate. So get 1, then eliminate. Okay? Then we'll go to the next column and we'll get a 1, and then we'll eliminate underneath. We'll get a 1, we'll eliminate underneath, etc., 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 until we're done. I already have a 1, so I just need to eliminate underneath. How am I going to eliminate things? Well, there's two different steps I'd like to do. I'd like to eliminate this 3, and I'd like to eliminate this negative 1. The negative 1 is pretty easy. I'll just take row 1, and I'll add it to row 3, and I'll put that into row 3 spot. That is going to be 1, 2, negative 3, negative 28, added to negative 1, 1, negative 1, negative 5. When I do that, I get 0, 3, negative 4, negative 33. I'd also like to go ahead and take negative 3 row 1s, add them to row 2, and put them into row 2's spot. So that means I'll have negative 3, negative 6, 9, 28 times negative 3, let's see, 60 and 24, so 84. Feels right. And then negative, or positive 3, excuse me, negative 1, 2, and 3. Add these up, you get 0, negative 7, 11, 87. Alright, so what that leaves me with is the following matrix after this step. I have the matrix. The first row I didn't change, 1, 2, negative 3, negative 28. But the second row and the third row I did. The second row is now 0, negative 7, 11, 87. And the third row is 0, 3, negative 4, negative 33. Now I need to try to get a 1 in our first spot here. So in my head, what I see is I have a negative 7 and I have a 3. To get it as a 1, if I multiply this all by negative 1, it would become a positive 7. If I multiply this all by 2, negative 2, it would become a negative 6. And then if I add a 7 plus a negative 6, I get a 1. So what I'm going to do is I'm going to say negative row 1, or excuse me, row 2. And I would like to add in negative 2 row 3s, and I want to put it in the row 2 spot. Negative row 2 is 0, 7, negative 11, negative 87. Negative 2 row 3s is 0, negative 6, positive 8, and positive 66. And when I add those two things together, I get 1, negative 3, and negative 21. So my new matrix is 1, 2, negative 3, negative 28. And in row 2 spot, I have 0, 1, negative 3, negative 21. And in the last spot, I have 0, 3, negative 4, negative 33. Alright, I have a 1. I got zeros underneath. I have a 1. I'd like a 0 underneath. To do that, I'm going to take negative 3 row 2s, and I'm going to add them to row 3. I'm going to put it in row 3. So I've got 0, negative 3, positive 9, positive 63, and 0, 3, negative 4, negative 33. Add those together, you get 0, 0, 5, 30. Updated matrix. 1, 2, negative 3, negative 28, 0, 1, negative 3, negative 21, and 0, 0, 5, 30. Alright, I got a 1 with zeros underneath, a 1 with zeros underneath. This is not a 1. So to get that, I'm going to multiply row 3 by 1/5. and I'm going to put that in the row 3 spot. And that leaves me with my final matrix that's in row echelon form of 1, 2, negative 3, negative 28, 0, 1, negative 3, negative 21, and 0, 0, 1, 6. There it is. I have that thing in row echelon form. All right, let's go on to another example. So we've seen what Gaussian elimination looks like. Let's talk about what Gauss-Jordan elimination looks like. It is where the first non-zero element of each row, and if I have is a 1, and if I have a 1 as my leading term, right, then everything else in that column needs to be a 0. So basically, I still have where it's upside down triangling, but I want to add to that instead of it just being like we were here, right, where we had just zeros underneath, I want to extend that to where I also have zeros above. Okay, same row operations that we did before. A reduced row echelon form, by the way, is unique for each matrix. So it doesn't matter what order you or your buddy goes in, you're going to end up with different ones for the reduced row echelon form. For row echelon form, you and someone else could both do row operations that are all valid, and you could end up with different answers. Now, once we do this reduced row echelon form, solving the equation is going to be really easy. Okay, and I'll show that to you in our example. So we want to take this example here. I want to put that system into an augmented matrix, and then I'd like to try to solve this thing using the Gauss-Jordan elimination. So I've got 1, negative 1, 1, 0, negative 1, 2, negative 3, negative 5, and 2, negative 3, 5, 8. Alright, first thing I'd like to do is take row 1 and add it to row 2 and put that in row 2 spot so that I can get rid of the x variable here. I'd also like to take negative 2 row 1s. I'd like to add those to row 3, and I'd like to put that in row 3 spot. So we'll do a little bit of workout space over here. I have 1, negative 1, 1, 0, and negative 1, 2, negative 3, negative 5. I'm adding them together to get 0, 1, negative 2, negative 5. When I take negative 2 row 1s, I get negative 2, positive 2, negative 2, 0. I'm going to add that to 2, negative 3, 5, 8. And that gives me 0, negative 1, 3, 8. So our new matrix is row 1 stays the same, 1, negative 1, 1, 0. Second row is 0, 1, negative 2, negative 5. Third row is 0, negative 1, 3, 8. Now I have a 1 with zeros underneath it. I'd like to get this one with a 0 underneath it. So to get the 0 underneath it, I'd like to take row 2. I'd like to add it to row 3. I'd like to put that in the row 3 spot. That means I'd like to take and then I'd also like to get a 0 above. So I'd like to take row 2, I'd like to add it to row 1, and I'd like to put that in the row above. So my two pieces of math to work out here are 0, 1, negative 2, negative 5, added to 0, negative 1, 3, 8, gives me 0, 0, 1, 3. And when you do it to the one above, we have the row 2, which is 0, 1, negative 2, negative 5, and I'd like to add that to 1, negative 1, 1, 0. Gives me, 1, 0, negative 1, negative 5. Rewrite my matrix as 1, 0, negative 1, negative 5. Row 2 stays the same. And row 3 changes into 0, 0, 1, 3. So you can see now I have a leading coefficient of 1, 0 underneath, leading coefficient of 1, zeros above and below, and a leading coefficient of 1. I just need to get the things above it to be a 0. To do that, we're going to take row 1 and add it to row 3 and put it into row 1 spot. And I'm going to take row 2 and add it to 2 row 3s, and I'm going to add that in the row 2 spot. Oops, need to do my math first. Row 1 and row 3 is 1, 0, negative 1, negative 5, and 0, 0, 1, 3, which is 1, 0, 0, negative 2. Row 2 and 2 row 3s is 0, 1, negative 2, negative 5, added to 0, 0, um, 2, 6, and you get 0, 1, 0, 1. So our final matrix is 1, 0, 0, negative 2, 0, 1, 0, 1, and 0, 0, 1, 3. This has put this thing into reduced row echelon form. Then they'd like me to solve this equation. Well, check this out. If I rewrote this, going back from the augmented form back to an equation form, you'd have 1x plus 0y plus 0z is negative 2, or x is equal to negative 2. You'd have 0x's plus 1y plus 0z's is equal to 1, or y is equal to 1. And you'd have 0x's plus 0y's plus 1z is equal to 3, or z is equal to 3. And I have my answer. So Gauss-Jordan elimination leaves me with a matrix that is really easy to solve. Okay, I'm going to skip through this one and this one and this one right now and say that we're going to stop the video here. We're getting close to 30 minutes. I don't want to overwhelm you. If you'd like to see more examples, let me know. I'd be happy to work them out.